Okay. Okay. So I think we can start. So in the last lecture, we started discussing about autoregressive diffusion model, and not autoregressive generative model, not diffusion model. And in autoregressive generative model, we kind of talked about two broad algorithms. One is the NAD, which is the neural autoregressive density estimation. The other one was fully visible sigmoid belief network, or FVSBN. These are the two algorithms we talked about in our last lecture, but we did not, and we only talked about primarily black and white images, which is like binary. Each variable is binary, it's black and white, so Bernoulli, and that is what we talked about. Towards the end, I very briefly touched upon non-binary discrete, and similarly, very briefly, I touched upon continuous. So today we'll start with that thing only. We'll start talking about non-discrete, non-binary discrete, and we'll talk about this continuous. But before we start, and then we'll go into the training algorithm. I mean, how to train this model. So we did not talk about training of this model. We only talked about how this model looks like. So we'll also be talking about how to train these models. Okay. Now, one thing is that not related to this, maybe. So I have not yet uploaded the videos and the lecture notes. So I'll do it this week. So I was traveling and so I could not. One video might not be uploaded immediately, which is I think lecture 3, because if you remember, the screen was not getting displayed and all of those things. So I have to do some editing, bring the screen and all of those things. So that might take some time. Everything else I'll upload this week. Lecture notes, everything, and video all except one. I'll upload it. Okay. So yeah, I did not get time. I was moving around. Okay. So with that, let us start, and let us start with a quick recap of autoregressive diffusion, autoregressive generative model. It has been 1 week because we did not have any lecture on Friday. So let us quickly recap that and then we'll proceed. Okay. Okay. So with that, quick review of autoregressive generative model. Right. And in autoregressive generative model, the idea is you will use the chain rule of probability, which is repeated application of the product law, and that will give you the autoregressive expression, right? So the idea is, very quickly, you will decompose the joint distribution in some autoregressive manner by using the chain rule. And remember that uh, which one is your x1, which one is your x2 might not have any meaning. Let's say if I'm doing it for image, it's a choice. You will have to choose which one is your x1, which one is your x2, which one is your xk. But if you're doing it for time series kind of model, you know what is your x1, x2, x3. So there will be some data for which this sequence will be obvious. Any speech, any NLP kind of problem, any time series modeling. In that sense, x1, x2, xk will be obvious. But if it is an image, in that case, this x1, x2 is not obvious, and you have the freedom to choose. Theoretically, it does not matter. Practically, because you will learn, there will be, though that will become an hyperparameter. Okay, but theoretically, it really does not matter. And then in Last lecture, what we said was that all of these are binary because we were dealing with black and white MNIST. And so we said that we are modeling these distributions using Bernoulli distribution, right? Because success or failure, 0 and 1, black and white. And then the parameters of the Bernoulli will be determined by using some machine learning model. The parameters of the Bernoulli, which is P, will be determined by using some machine learning model. And that some machine learning model is what decides whether it is fully visible sigmoid belief network or NED. If it is NED or neural autoregressive density estimation, then we know that that machine learning model is a single hidden layer neural network. And if you are using fully visible sigmoid belief network, then we know that that model is a logistic regression. So depending on what machine learning model you are choosing for expressing this conditionals will decide what algorithm you are using, right? So this also tells you that there are definitely other variants of autoregressive generative models. Why is it that you will be limited to only a single hidden layer MLP or a sigmoid or logistic regression? That is not necessary. Why can't you use an advanced neural network model like a transformer, like RNN? Actually, you can. Even autoencoder. You can use autoencoder within this to model these things. And if you use those, then the name will change. So my idea is that we will not go into that today. I might give you some glimpse of that towards the end of the lecture today. But we will probably come back to that, specifically the transformer one, at the end of this course. Because when you bring transformer into this, that is your GPT. GPT uses autoregressive model plus transformer. That is what GPT uses. But to do that, I will need to spend 3-4 lecture on transformer itself, which I don't plan to do right now. So we will not be doing that. But we will be touching upon GPT, which is probably the most famous generative model, towards the end of this course. So at that point, we will spend maybe 2 weeks on just GPT. And at that point, we will come back to this autoregressive model. We will cover transformer from scratch to a certain extent. And then we will talk about how to combine the two. And that will essentially be designing your GPT model. Okay, so we'll be doing that, but at the end, that is the last thing we'll do in this course. But I'm telling you from now, it's a spoiler that this is the foundation for GPT. In GPT, it is generative pre-trained transformer, right? So generative comes because of autoregressive, pre-trained because the model is pre-trained, transformer because you use transformer within the autoregressive. That's why you call it generative pre-trained transformer. The name GPT comes from the fact that it's a generative model, you use transformer within the generative model and it's pre-trained. So that's how it the name actually comes into picture. Yeah. Yeah, yeah, yeah. This formulation is generic, right? It is arbitrary only. So this is the most generic formulation you have, and this stays. You generally don't make it Markovian, for example. You will not make it that x5 is only dependent on x4. Because you can imagine that if it is a language, the fifth word only depending on fourth word is very restricting. It will make no sense. So we will not want to do that. We will rather want something where it is sufficiently long. So we won't do that. Okay, at least in this one. Okay. Anyways, so coming back, these are things for the end of the course, right? So this was the the autoregressive scheme or autoregressive generative model that we talked about last time, and we said that for binary, so we also said that for binary features, P of, let's say, xj given x of 1 to j minus 1, so I am writing this one, is modeled as Bernoulli, right? This is what we discussed last time, and because we model it as Bernoulli, it is either success or failure, and that is why it is this logistic, or this is, let's say, this I mean, neural network with the last layer as sigmoid activation and so on and so forth. Okay. So now this is what we have discussed already, right? So now the first thing is that what happens if the features are non-binary discrete? What happens if the features are non-binary discrete? How do you model it? Because whatever we talked about was for binary, and the fact that we are working with Bernoulli is only because it was binary. So can you think of an example where it will be non-binary discrete? Any example, any data set where it will be non-binary discrete? Colored image. Colored image is RGB continuous from 0 to 255. So that's a very easy example, right, where it is non-binary but discrete. It will take value as 0, 1, 2, 3, 4. You can go up to 255. You have 3 channels, R, G, and B, and so it's 256 features are there. I mean, each feature is 256 dimensional possible, right? And cross 3, you can say 256 cross 3 as well, right? So yeah, that is one example, and you can think of others also, but that is a very easy example to think about. That is the example that all of you have heard of, right? Now, in this case, what you do is very simple. You basically model the last layer using a softmax activation function. Okay, so basically in this case, what we'll do is, in this case, what you do is, first thing is the conditionals, right? That is the first thing to do. But the conditionals are modeled as multinovely or categorical distribution, which are basically synonyms, by the way. Categorical distribution. Now, I did not review the categorical distribution, but can you guess what is the PDF of categorical distribution, or PMF, not PDF? What is the PMF of categorical distribution? Any idea? Think about throwing a dice. What will be the PMF of that? It's an extension of Bernoulli, quite obviously. But what will it be? Uniform. It's categorical. I mean, I'm giving the name. I'm asking the PMF. I'm not asking the distribution. What will the PMF look like for a distribution where the output is more than 2? When it is 2, what is the PMF look like? P to the power x, 1 minus p to the power 1 minus x. That's what it looks like. But now it is not 2, it is k. If it is k, how will it look? How will it look? I mean, column vector you don't write. What is that column vector? I don't know. You have to give a proper answer, right? So what will the Dirichlet distribution, the multinovely or categorical distribution, what is the PMF of that? Think about throwing a dice. How will it look? Not indicator function, not identity. So it will be simple. It will be pi to the power xi, I equal to 1 to k. It will be pi to the power xi, I equal to 1 to k. product of that, obviously. And there is a constraint associated with that, that summation of pi should be equal to 1. So think about throwing a dice. In that case, probability of getting head multiplied by you got a head, not head, probability of getting 1 multiplied by you got a 1, not multiplied, power. Then probability of getting a 2 to the power you got a 2, dot dot dot, probability of getting a 6 multiplied by you got a 6, and probability of getting 1 plus probability of getting 2 plus probability of getting 3 plus probability of getting 4 plus 5 plus 6 is equal to 1. So the multinomial distribution looks like this. So the multinomial distribution, PMF of multinomial distribution, it looks like fxx is equal to product of I equal to 1 to, let us say, k, which means there are k possible outcomes, and then you have your pi to the power xi, and the constraint is summation over I pi is equal to 1. So how many parameters are there in this case? What is the number of parameters? K minus 1, because the last one is dependent on the remaining. K minus 1, not k. And now you can see that if you put k equal to 2, it will give you exactly the Bernoulli. If you put k equal to 2, you will recover the Bernoulli, because in that case xi is x and x1 is x, x2 is 1 minus x, right? So you will recover that. Now what is this x here? X is the random variable, obviously, but how does this x looks like? Because that is important, otherwise this will not hold. So let's talk about throwing a dice. If you throw a dice, what is the outcome? 1 to 6. So you will not write 1 to 6, you will write it as one hot encoding. So if you get 1, it will look like 1 0 0 0 0 0. If you get a 3, it will be 0 0 1 0 0 0. Now you put it here, you will realize what is happening. This only holds when you have written the random variable as one hot encoding. So let me write it down, where random variable, let's say outcome, is equal to x1, x2, xk. Okay. So example, consider throwing a dice, and in that case your, let's say, your sample space is 1 5 3 3 2. Let's say this is your sample space. I mean, not the sample space, this is the actually the data, sorry, not sample space. Sample space is 1 to 6, obviously, this is a data. So you have performed experiment and this is the data, this is what you have observed. So your x1, if I have to write x1, right, so the first observation, this actually looks something like 1 0 0 0 1 2 3 4 5 6, but this one is actually your x1, this one is actually your x2, this one is actually your x6. This is how you represent a random variable, and when this is how you represent the random variable, you will only get 1 in one of the location, everything else will be 0. You cannot get in a throw of dice 2 and 3 at the same time, or any 2 or any 3 at the same time. You will get only one outcome, and that one outcome location will become 1, everything else will become 0. So now if you take one of this, let's take 3, right? Take the 3 and put it there, what will you get? P1, which is probability of getting 1 to the power 0. P2 to the power 0, P3 to the power 1, P4 to the power 0, P5 to the power 0, P6 to the power 0. So you get 1 times 1 times P3 times 1 times 1 times 1. So you get P3. What is P3? Probability of getting 3. You see what is happening? This is your categorical distribution. This is your multinomial distribution. Clear? Please read more about multinomial distribution. Remember, we discussed the maximum likelihood estimation and how we can use maximum likelihood estimation to find out P in a Bernoulli, right? Same thing you can do in multinomial. It will be little bit more involved because there will be an additional constraint that will come into picture, but you can reach that common sense answer even in that case. You can try it on your own, assume some outcome and then do it. You will get the exact same result here in a generalized sense. Any question? What do you mean by ordered? Okay. So then if this you change, you have to change P1, P2, P3, P4 as. In that case, P6 also should be the first one. If 6 is what you call as 1, so if 6 you are writing 1, 0, 0, 0, 0, 0, then P1 should be probability of getting a 6. This D, data. Oh, NCX is not there because it is multinomially, not multinomial. In multinomially, just like Bernoulli, you are interested in what you will get when you throw a dice. In multinomial, just like binomial, you are interested how many times you will get head or how many times you will get tail. In that case, that NCX term you are talking about will come appear. So that will be the multinomial. And in that case, you are not interested in the outcome of your experiment. You are interested in how many times you will get. So that's the difference. Okay. So that is the exact difference between Bernoulli and binomial. This is multinomially. Then there is multinomial also that will exactly appear. But in our case, we'll mostly be needing this one. Okay. Any other question? Is multinomially clear? Please read about it. There are additional derivations which you can do on your own. This will be, I mean, that will help you clarify this concept even further. Okay. Anyways, this was a detour. Let us come back. What I said was the conditionals are modeled using multinomial or categorical distribution, right? Which means go back to the autoregressive one, right? In autoregressive, what was you having? You were having P of x1, x2, xk, right? Remember, this xk is the kth feature, not the outcome. This xk itself can have 3 or 4 outcomes, in ideally 256 outcomes in this case, if it is an image. So don't confuse this xk with this small xk that I wrote. Small xk is in a single location, what is the outcome? Is 1, 2, 3, 4, 5, 6, right? Please leave. In small xk in the previous one, that is basically denoting that at a single location, let's say image, at a single location, what is the pixel value? It is 0, 1, 2, 3, 4, 5, 255. That's what it is denoting. This capital XK, this X is denoting the location itself. Is it the top corner, bottom corner, center, which one? So if I talk about the colored image, let's say, of dimension 28 cross 28, then this capital K goes up to, in this case, 784. Where each of the 784 can take 256 values, actually 256 cross 3 values, I mean 3 channels, right? So that distinction, please be very careful about, because I'm using K, don't get confused. Okay. So this is what these pixel locations, and this is equal to product I equal to 1 to capital K, P of xi given x less than I. Now, in this case, my P of xi given x less than I, this will be modeled as a multinomial categorical, okay, as a categorical distribution of xi given some parameters of the which is the p's. So, let us call it p's, maybe we can use p is we are using, let us use alpha, right, alpha of x less than I, okay. So, this is basically a categorical distribution over xi where the parameters are function of previous x's, right, and this parameter you will write it as, any idea how the parameters I will write? It will be neural network of x obviously, but I want to write it as the last layer. So, last layer previously I was using sigmoid, remember sigmoid I was using, now I will use softmax. So, this will be softmax of so alpha I use, so let us use theta now. So, theta I so theta I2 let us call it, okay, theta I2 transpose H I plus okay, plus the beta term is there, I am not writing, the bias, okay, the bias will be there, I am not writing it, okay. And what is H I equal to? Where H I is equal to, it will be now sigmoid, not sigmoid, sigma. Sigma means activation function. It can be any activation function. It can be ReLU, ELU, GELU, MIS, sigmoid, whatever you think is good. So, there is no constraint on the activation for the first layer. There is obviously constraint on the activation of the last layer because it is a categorical multi-class. So, Hi will be equal to sigma, which is a nonlinear activation function. It is not sigmoid. It can be sigmoid, but it is not compulsory to be so that it should be sigmoid. So, sigma, and then what is inside is theta I1 transpose x less than I, right? Again, B I am not writing the bias. Okay. So, fundamentally what has changed from what we discussed last time? There is only two changes. The first change is that you are now using softmax instead of sigmoid. That is the first change. The second change is that distribution is now categorical instead of Bernoulli. There is no other change, everything else remains the same. And remember, I am talking about NED here. This is the neural autoregressive density estimation, this NED. If it was fully visible sigmoid belief network, well, that is only actually only works for binary case, but you can also think of using that as a single layer multi-class. So, basically replace the sigmoid with softmax, that will still work, but so basically in that case it's a single layer, no hidden layer. So, a classification, but a multi-class classification, and if you do that, that is work, that will work, okay. So, I will repeat, this is exactly same as what we discussed last time, which was the binary case, now is the non-binary case, apart from two changes. Change one, distribution is now categorical instead of Bernoulli, and that is quite obvious, generalization of Bernoulli to more than two outcomes is categorical. The second one, because it is categorical, it has more parameters. Because it has more parameters, the output of the network is having an activation function softmax and not sigmoid, and that is the only change. And with softmax, you can see that automatically summation of pi equal to 1 will be satisfied. Can anyone tell me what is the softmax activation function? What is the expression for that? E to the power minus x divided by summation of e to the power minus x. All possible values of x. That's what softmax is. And because of this formulation, you can see that the summation equal to 1 will automatically hold. Okay. Exponential of the minus of the parameter divided by summation of all parameter value. Okay, that's the softmax. I'm not writing it, but that's what it is. Any question on the non-binary case? Inside the alpha. So hi is function of what? All the inputs, right? And what are the inputs in this case? x1 to xi minus 1. So that is why, right? The input nodes. So x minus I are the input nodes, right? So that's why. Okay. Any other question? Give example. Hmm. Hmm. It will be vectors. I mean, it will not matter. Ultimately, it's how you are coding it, right? But mathematically, it does not change anything. So it will not matter. Okay. So yeah, so that is actually fine. Because it is NAID, so single layer. I mean, again, remember that NAID is only one of the autoregressive, so you can use more layer, no one is stopping you. But then you should not call it NAID, that's all. Okay. That is the only requirement. So that is because those who developed NAID, they designed it as a single hidden layer. So when it is single hidden layer, we call it NAID. But the name itself is not restricting to single hidden layer actually. Neural autoregressive density estimation is not saying single layer neural or what. So you can use, no one is stopping you, and that's people have used it. It's just that the original researchers who developed it, they used single layer. Okay, and remember the parameter sharing part that still holds. I'll come back to this in a short while, but last time we did parameter sharing, right? So that holds here as well. In the original one only they did. Okay. Okay. This is clear? Clear? Okay. So this is clear. Let us go to the next part, which is continuous. Right? So the next part is what happens if output feature is continuous. Right? This is also a possibility. Any example where the output feature will be continuous? You can leave. Hmm? Stocks, yeah. Please leave. Stock, obviously. Anything continuous, right? Even speech. Speech is also sound, so it's NLP is not, because then it's discrete. But speech is like a sound, right? So that is continuous. So actually, most things are continuous, I believe, right? Stock, weather, climate, temperature. I mean, whether it comes time, temperature, wind speed, whatever you think about, right? Speech. So there are many examples of that. So what happens if the output feature is continuous? Any guess? Any idea? First, the distribution. Hmm? Correct. The distribution has to be continuous. So it will be a PDF, no longer a PMM. The question comes, what PDF? Because previously we could categorically say it is categorical distribution or it is Bernoulli distribution, because we knew what is the number of features, right? But now it's continuous. Continuous, there is a hundreds or many, actually many distributions, right? Continuous. Which distribution should I use? Why Gaussian? But what if the data is having multiple modes? That's a good point. That Gaussian, because it goes from minus infinite to infinite. Well taken. But what if it has multiple modes? Mixture of Gaussian is a good choice actually, because that addresses the limitation. But that has its own problem, which is how many Gaussian, how many mixtures. I mean, you don't know. You can take too many and hope that it will collapse, uh, and all of those things are possible, but it has its own challenge. Continuous data always is challenging. I mean, as simple as that. But yeah, mixture of Gaussian is the most popular one. The reason being advantage of what he said and what you said. You combine the two, you get mixture of Gaussian, right? So what happens when the feature is continuous? Again, two changes will come into picture. The first one is, the first change that will come into picture is that the conditionals will be continuous distribution. Okay. Now it can be any continuous distribution. If you know and if you have knowledge about how it looks, you can use a more informed continuous distribution. For example, if you know it is symmetric and single mode and the support is not unknown, then it's a Gaussian. You should not use mixture of Gaussian. If you know it is skewed in one direction, then you use some skewed distribution like extreme value or something like that. If you know it has multiple modes, then you should use mixture of Gaussian. But if you don't have any knowledge, then mixture of Gaussian is a good choice because it can collapse to a single mode and it can have multiple modes, right? So in that sense, it's a good choice. Mixture of Gaussian. Okay. So you have to select it. One popular choice is mixture of Gaussian. It's not the only choice, obviously. Okay. So the conditionals will be continuous distribution. One popular choice is mixture Gaussians. How does the PDF looks like for mixture of Gaussian? Fxx, it will look like summation alpha I, a Gaussian of x with mean mu I, variance sigma I square. I equal to, let's say, 1 to, I don't know, p maybe. Okay. So this is the PDF of mixture of Gaussian, which is as simple as adding p Gaussians. PDF, not the variables. If you add variables, you will get something else. You will get a Gaussian itself. Don't add the random variables, add the distribution. Okay, so be careful with that. And obviously, summation of alpha I will be equal to 1, normalizing, right? So summation of alpha I would be equal to 1. So one option is 0.5, 0.5, one is, yeah, it can be whatever, right? 0.7, 0.3, 0.1, 0.1, 0.1, 0.1, 0.1, up to 10 times. All of that are possible. Yeah. Can we always? Not exactly. What if it is skewed? Single mode and skewed. Then obviously the modes will collapse, you will get a single mode, but the skewness will not come. So there are cases where you can imagine that this will probably not work, but this is the most flexible one, let's put it that way, right? In fact, if you think about it, if you could always take this, then you don't need a generative model course. You will always take it to a mixture of Gaussian and fit parameters. You will not need a course on generative model, right? Obviously, you cannot always take it. But this is among the known ones, one of the most flexible ones. Clear? So how mixture of Gaussian looks like? Let me try to draw. I will draw a very bad diagram, but bear with me. And I know I will draw a bad diagram because I know how it draws. I mean, I know my own drawing, right? So let's say this is one component. Okay. This is another component. The mixture of Gaussian will look something like, not exactly, but something like. Obviously, keep in mind that the area under the curves will be equal to 1. So that's why I'm using the term something like. Because the way I've drawn it, it is not 1. So the height will basically go up and down, but it will look something like, it will have multiple modes and all of those things, right? So basically, you can see that when I combine these two, I get a bimodal distribution. And obviously, there are two Gaussian components here. Let's call it, this is characterized by mu2 and sigma2 square, whereas this one is characterized by mu1 and sigma1 square, right? Clear? And now the center of this individual Gaussians is controlled by, the location of this Gaussians is controlled by the means. The spread is controlled by the variance, and the weightage is controlled by alpha. So you have 3 parameter per component. One is, what is the weightage of a component? That is controlled by alpha of that component. What is the location of the peak? That is the mode, and mode and mean coincides for this distribution. So that is controlled by the mu I. And then what is the spread? It is very small, very large, the variance, right? That is controlled by the variance. And you can imagine if this mu1 is equal to mu2, you will go to a single, I mean, unimodal kind of thing. That's what you will ultimately get. But sigma 1 can be still different. And even if sigma 1 is different, sigma 1 is not equal to sigma 2, you will still get a unimodal. If this mu's, how far apart they are, will determine how many modes you have. They are close by, you will see the mode and then something, two modes very close. If mu1 and mu2 are well separated, you will see it is going, then coming to almost 0, and then again a mode is coming. The more separated mu1 and mu2 are, it becomes difficult actually to track that distribution, because you will get a almost 0 region in between. So it becomes more difficult. But this is how mixture of Gaussian looks like. So now, with the concept of the mixture of Gaussian, now what you can do is, you can go back and look into the autoregressive generative NAD and see what are the changes we are going to do in NAD, right? So to model or continuous features, your probability of x1 to xk is equal to product of I equal to 1 to k, p of xi given x less than I, right, where p of xi given x less than I is modeled as a Gaussian, or rather mixture of Gaussian, sorry, is modeled as a mixture of Gaussian. Let's write j equal to 1 to p alpha j Gaussian of xi given mu j comma sigma j square. Okay, where this mu j and sigma j are function of x1 to I minus 1. Alpha j can also be function of, but in the original implementation they took alpha j to be all to be equal weightage, 1 by k or 1 by p in this case. Okay, but you can take even alpha j to be output of your neural network. No one is stopping you from doing that, but let's go with the original one. So in that case, mu j and sigma j square will become the output of my neural network. Or so basically one more line will come here, which is mu comma sigma square will model and I'm not writing j here because for all j's, I mean each j it will be a neural network. So maybe I should write j. Let's write j. Actually all, that's fine. In fact, you know what I should do? I should write it as alpha ji mu ji sigma ji, right? Otherwise it is confusing. They are not the same. So mu ji, alpha j and sigma j. And now mu j and sigma j are vectors, right? Because that is mu j or mu I, right? Mu I. That means these are vectors containing for all j's. So again, I will go back to that. Imagine the MNIST data set. How many locations are there? 784. So this xi, that I goes from 1 to 784. Now at each of this location you have continuous now, and that continuous we are modeling using mixture of Gaussian with j components, p components. So that j goes from 1 to p. So at a given location you have p components, and you have 784 such locations. Now at that location you have p components, so you have 2p parameters, mu and sigma 2 per. So 2p parameters, right? So that's those 2p parameters, p plus p is written in this form mu I, which is a vector of p parameters, sigma I square, which is a vector of p parameters. So you have 2p parameters. If I take alpha also, then I will have 3p parameters. Is this clear? I'll repeat once more. You have, let's say, k locations. Think of the MNIST 784. But now it is not MNIST, so at each of this location it is continuous value, not binary. So this I goes from 1 to 784, right? Now for each of these I, it's a continuous, or using a mixture of Gaussian. So that mixture of Gaussian has p components. So if it is p component, each Gaussian component is having two parameters, actually three parameters, mu, sigma and alpha. Out of that I am taking two. So each of the p, each of this is having two parameters. So p component will have two p parameters. This is for a given a k, given I. And this again varies from 1 to k. So your total parameter will come out to be 2p times k. Okay. But again, these are parameters. Now neural network parameters will come into picture. Each of these will have to be modeled using neural network. Clear? Hmm. Exactly. That's what I was saying, right? You will not know how many Gaussian component to use. This is more like a hyperparameter, not a parameter. So you will have to select that and manipulate that. So in that case, okay. So that's why mu I and sigma I square is what you will get as a function of x1 to I minus 1. X less than I is 1 to I minus 1, right? And so what will it look like? It will be let's say sigmoid, not sigmoid, activation function. And I'll tell why I'm writing activation function. I'm not writing the index, but you can imagine some theta transpose x less than, not x, h will come into picture, right? And then h will be again some sigma 2 1 theta 2, so let us say theta 1 transpose x, right? And this sigma, what should it be? Any idea? It's a continuous, so most of the time you will be taking linear, because mean can be negative, positive, you don't know. But you have to be careful with sigma, sigma cannot be negative. So better is whatever you are getting, take a square of that and call that sigma. Because sigma cannot be negative, but if you take ReLU, then you are taking ReLU separately, then mean you have to be separate activation and that. So in the same layer, different activation will come and that will create problem. So the better way is that take it to be linear. So mean is fine. Sigma can be negative. So what you are getting is actually square root of sigma, and then square it, that is your sigma. Okay. For ReLU, you cannot have zero negative, right? So then mean will be, mean can be negative, right? So mean will not be negative in that case if you take ReLU. If you normalize it from 0 to 1, then it's fine. I mean, then you take sigmoid. Who is stopping you? If you normalize it from 0 to 1, then take sigmoid. But my point is that this one is much more flexible. There is no hard constraint on what to take in place of sigma 2 or sigma 1. Sigma 1, there was never any hard constraint. You could take anything even before. Sigma 2 is the one which was hard constraint. For the binary case, sigma 2 was always sigmoid. For the non-binary case, sigma 2 was always softmax. But now this will not be softmax, that is sure. But then what it will be, if you normalize, it can still be sigmoid, because sigmoid will give you continuous value between 0 and 1. Or it can be linear, or it can be ReLU. Depends how you are normalizing your data, what range it is in. So much less constrained on sigma 2. Sigma 1 was always kind of free, you could take, right? Any question? You can and cannot, because in Gaussian, no matter what parameter you bring, it will not control the skewness. In Gaussian, right? But that is known for Gaussian. That will be a function of your mu and sigma. So you have to take a mixture of, let's say, a Gaussian and an extreme value. That you can do, but then that makes your life much more difficult, and all those things will obviously come into picture, right? Your reparameterization scheme and all of trick will probably not work. So yes, you can do that, but it's not so straightforward. That's all I will say. Okay. Okay. Any question? No? So I'll repeat once more. So the difference between binary, non-binary, and continuous is very simple. First is your distributions will change. For binary, it is Bernoulli. For non-binary, it is categorical. For continuous, it can be any continuous distribution, but let's say mixture of Gaussian. That's the most common choice, right? This is the first change. Second, the neural network last layer will change. For binary, it is always sigmoid. For non-binary, it is always softmax. For continuous, you have some freedom, but it will not be, let's say, softmax. Let's put it that way. Okay? That's the whole difference. Nothing else changes. I'll repeat once more that this is we're talking about only NAID and this thing, but the same concept holds for others also. If I go from NAID to, let's say, MAID, there is an algorithm called MAID also, which is masked autoencoder density estimation, MAID. Okay. So if I go from NAID to MAID, all of this thing holds. The only thing that changes is the neural network architecture. In neural network, you use a mask autoencoder. Now, what is mask, what is autoencoder will come later. So, don't worry about that. Just think that we are using a different neural network architecture. Okay. And because I don't want to cover autoencoder now, I am not going to cover MED. But I am just giving you an example. Similarly, generative transformer, if you go there, it's the neural network architecture that will change. It will become transformer. You can use a RNN also, generative RNN will come into picture. So you can use whatever you are comfortable with, and that will make it your generative ABC, where ABC can be your choice, right? So if the network architecture changes, the name changes. But the other concept is fixed, because the other concepts are concepts that relate to autoregressive generative model. Whereas this network and all of those things makes it a special case of autoregressive generative model. NAID, MAID, fully visible sigmoid belief, all of these are autoregressive generative model. Generative transformer, all of these this comes under the same family. So, but the members of the family are decided in many cases based on what neural network architecture you are using, or rather what machine learning model you are using. Because let's say in sigmoid belief network, fully visible, we are not using neural network at all, and that's fine. Okay. Okay. So now I have half an hour, and now we will go to the training part. How do we train this model? What is our loss function, and how do we find out the parameters? Remember the stochastic gradient descent we already discussed in the practical. So I will assume that you know stochastic gradient descent. I will only talk about the loss function basically. Okay. So the question is, how to train the model? Can you remind me what is the goal in autoregressive, or not autoregressive, in generative model in general? To learn the distribution. Distribution of what? The distribution from which the data is coming. So then what should be the goal, learning goal? That the distribution that you are getting from the autoregressive model should match as closely as possible with the distribution from which the original data is generated. So you basically will like to match two distributions, right? Everyone follows? Correct? So if that is the case, then what should be my loss function? KL divergence. We have discussed about it. That is one of the possible loss function. That is the most popular loss function. That is what we are going to use. But again, remember that as I said that different models use different neural network architecture. Similarly, there are different models that use different divergences also. For example, you can use alpha divergence, and there are other divergence, you can use that also. There is also, I think, maximum max mean discrepancy, MMD, that also can be used. So there are different things that can be used, but the most popular one is the scale divergence. Okay. So how to train? So first of all, as I said, we want the distribution obtained from uh, autoregressive generative model, let's write it GM, to match the distribution of the data. That is what we want, right? So distribution of the data, that is one part. Let's call it P data X, where X is my sample, okay, sample from the variable X. And then autoregressive generative model. So I have this part also. Maybe I will use another color. Distribution obtained from autoregressive generative model. Let's call it P theta of X. Any idea why P theta of X? Theta are the parameters of the neural network or the logistic regression, whatever, I mean, same thing. So P are the unknown parameters of the network of the machine learning model, because those are the only thing that is unknown. If you know the network parameters, you can use it to find out the distribution parameters. If you know the distribution parameters, the distribution is known. Example, in case of Bernoulli or binary case, if you know the neural network parameter, you know what is P, probability of success. If you know what is probability of success, you know the PMF. In case of Gaussian mixture, if you know the distribution, if you know the parameters of the neural network, you know what is alpha and what is mu and what is sigma, which means you know what is the P, the conditionals, right? So what is unknown? The network parameters. And that is what you will be finding. Network parameter means weights and biases. W transpose X plus B, the W and B. Okay. So that is the only thing that is unknown. Clear? So this means, so one obvious way is to minimize the divergence between the two, right? It is an obvious choice. All of you told that it is scale divergence is an obvious choice. Scale divergence is a divergence. So that's an obvious choice. So which means I can write theta star, where what is theta? Parameters of the network or the machine learning model. I am repeating it so that you don't forget. Theta is the parameter of the machine learning model, which means the weights and biases. So theta star means the optimal one is equal to, you will like to minimize theta scale divergence between P of data X, P of theta X. What is P, by the way? P of data is PDF, distribution, not probability. Because I am not treating fx, so I think you can get confused. P of data is a distribution. Now, if it is discrete, distribution is probability, because that is mass function. But if it is continuous, then it's not probability, it's PDF. Clear? Obviously, we don't know. If we know that, we don't need to solve this problem. Coming to that. So here's a valid point. This expression needs P of data. If I know P of data, then why do I need a generative model? I will just sample it. P of data is not known. So I am in a situation where what I want to learn is sitting there in the loss function. So definitely I cannot work with it directly. I have to do some manipulation. I will do it. Clear? P of data is what I want to find. And that is something that is sitting in the loss function. Which means this is not solvable. I'll never be able to compute the scale divergence. And if I can compute the scale divergence, then the problem of finding p data does not exist. Both cannot happen at the same time, right? So definitely we cannot work with this loss function, but this is the fundamental. We need to do some modification to this to arrive at a position where we should be able to practically work with it, right? Clear what the problem is? Okay. So this is the KL divergence that we want to minimize, and whatever theta we get by minimizing is our theta. Remind me, what is the KL divergence formula? KL of P theta and P theta. Remind me, it is equal to what? Integration, first of all. Integration of P theta log of P theta by P theta. Obviously, each of this is having a x dx. This is the one which is also equal to expectation with respect to P theta, obviously, but I don't need that right now, so I will not write that. Okay. So this is the one I can, the log A by B is log A minus log B, I can do that and decompose it into two terms, right? So I'll do that. So this is equal to, the first term will be equal to P theta log of P data x dx. This is the first term. The second term is equal to minus P theta log of P theta x dx. Right? Now what can you observe about the first term? The first term has it some special property? Independent of theta. So I don't care about that term. So then what do I care about? The second term. So the first term is independent of theta, which means it is some additive constant. That's all. Because P theta is known. So if it is known, I mean, whatever, is independent of theta. So we drop it. So if we drop it, what is my objective function or what is my problem statement now? Theta star is equal to, you can either minimize with the negative sign or maximize excluding the negative sign. So let me write maximize. I at least have to write one negative sign less. Arg max theta, and then you have integration of P data x log of P theta x dx. Right? What is this quantity equal to? Statistical quantity. What is this? Expectation of log of P theta x. So this is equal to expectation of, I mean, x coming from P data, I mean expectation with respect to which distribution? P data, and then log of P theta x. Correct? Right? Now, law of large number, what does it say? We talked about law of large number and central limit theorem, right? Law of large number. What can you do? Any expectation can be represented in terms of the samples drawn from the distribution. Right? Now, do we have any sample from P of data? Yes. What are those? The training samples. We have training samples. Using law of large number, this expectation we are going to represent using the training samples in a discrete form using summation. Right? I'll again repeat. Any expectation can be represented using samples in a discrete form, in a summation form. That is what law of large number allows us. And if this number of sample is very large, then this tends towards the exact thing, true mean, right? So any mean can be represented using samples drawn from the distribution, and that's what law of large number allows us, right? So we are going to do that. So this is equal to, I'm using law of large number, not large language model, n not a m. Okay. So using law of large number, what we get? So I have, let's say, how many data points we had? N, right? We're using n data points from the beginning itself. So this is equal to 1 by n summation I equal to 1 to n. So these are your training samples. Log p theta x I, where xi is your ith training data. So if it is the MNIST image, it is your ith image, right? Clear? Now, can you tell me what is p theta x of I? What is this quantity? What is this quantity? In statistical terms, is there a name you can assign to it? It is the likelihood. It is actually p of x given theta. Theta is unknown. That's, if you put it on conditional side, that's the likelihood actually. So then what is this log of p theta? Log likelihood. And then you are taking an average of that. So it's a log likelihood. So you are maximizing the log likelihood or the likelihood. Log is convex, so it doesn't matter, right? So this basically minimizing KL divergence give the MLE solution. So although we are trying to minimize the MLE, what we are getting is the maximum likelihood estimation. We will either maximize the log likelihood or minimize the negative log likelihood, right? That's what we are essentially doing. This is your likelihood. Okay. So with this, we are not yet done actually, but whatever is done, let me summarize it and then we will proceed. With this, my problem statement now is theta star is equal to arg max theta. 1 by n you want to keep, you want to remove, you remove, doesn't matter. Log p theta of xi. This is I by the way, not 1. This is my new problem statement, right? Can we simplify it even further? Can we simplify it even further? Yes, we can, because we know that p of xi will be written as, any idea how will p of xi be looking like? Autoregressive. It's autoregressive, that chain rule will come into picture, right? P of xi is for, as I said, is for the ith data point, which if we think about MNIST has 784 features, 28 cross 28. I can use the autoregressive to write it in the chain rule. We are going to do that. By the way, I have done one assumption here. Can you tell me what is the assumption I did? There is one assumption I have done, written here or carried out, that the samples are IIDs. And the law of large number holds for IID only, by the way. So When I say it's the law of large number, that means I am assuming the samples are IID. They are not dependent. If they are dependent, then law of large number in its original form does not hold. There is law of large number for Markov, but that's a different thing. We will not go there. Okay. So remember, always keep in mind that we are going with the IID assumption, which is a very basic assumption, which means it is from the same distribution. It has to be. We're trying to learn the distribution. And the samples are drawn independently. That's all. Okay. Any doubt? Okay. So we're going to further decompose this thing, right? Let us do that. So P theta of xi. I'm taking only the ith sample. Okay. We know that this is equal to product of j equal to 1 to k features is what we assumed. I think k was 784 last time, right? So k is the number of features, number of points, number of pixels, 784, 28 cross 28, that is all k. So this is equal to p theta j, theta j. Actually, I should write theta j is fine. Yeah, p theta j. Then x. I will now start decomposing it. So product I have already written. X j I given x less than j I. Is this expression clear? What is p of x I? What is p theta of xi, left hand side? That is the joint probability of the ith sample. Now joint probability you can write as product of autoregressive. Is it not autoregressive? P of x1, P of x2 given x1, P of x3 given x2, x1, P of x4 given x1 to x2, x3, P of x5 given x1, x2, x3, x4, dot 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 P of xk given x1 to k minus 1. Now this I am doing only for the ith data point. So above all of this, the I is sitting. And theta j I am saying because each conditional is modeled using a separate network. So each conditional is having its own parameter. So that's why I am writing it theta j. I'll repeat. The left hand side, p theta of xj is the joint distribution evaluated for the ith sample. It's the joint distribution evaluated for the ith sample. Now xj, xi, right? Left hand side. What is the dimension of that? MNIST. What is the dimension? 28 cross 28, 784. Now how can I write it? P of 1 multiplied by P of x2 given x1 multiplied by x3 given x1, x2 dot dot dot. Now this whole thing, product thing, is the same thing I have written. See, xj given x less than j. So x1, x2 given x1, x3 given x1, x2 dot dot dot. Now this thing I am evaluating only for the ith sample. So on top of the x, you see a I sitting there, because this is only happening for the ith sample, not in a generic sense. And then with all of this p, you see a theta j there. Why? Because each of the conditional is modeled using a different machine learning model. That's why theta is a function of j, or rather theta has a suffix j, not a function of j, but as a subscript of j. I'll repeat once more because there are 3-4 things happening. First thing, it's a joint distribution evaluated at a given sample, and that sample is I. So I will sit wherever x is there because it is at that sample. Second, it's for a given sample. The sample is a matrix or a vector. It has k features. And because it has k features, I will use the autoregressive formula to write it, which is the chain rule of probability, which is P of x1 multiplied by x2 given x1 multiplied by x3 given x1, x2 dot dot dot. right? Now this x1, P of x1 is modeled using a different neural network. P of x2 given x1 is modeled using a second neural network. P of x3 given x2 and x1 is modeled using a third neural network. So all of these neural networks are having their own parameters. So that's why you see a theta j. That means these parameters are not same. Clear? Any doubt? Okay. So if this is okay, I can take it and plug it in the previous expression. And that will give me. So therefore, theta star. Now what is this theta, by the way? Theta is all the theta j written together. Theta is theta 1, theta 2, theta 3, theta k. So all of these thetas together is theta j, theta. Remember, theta 1 is not a single parameter, that itself is a vector, right? Theta 1 is itself a vector, theta 2 is itself a vector, theta k is itself a vector. So it's a very big vector we're talking about. Okay. So theta star is equal to, we are doing maximization if I remember correctly, argmax of theta. I think there was 1 by n summation I equal to 1 to n, and then there was a log, and then this product comes into picture, p theta j x j I x less than j I. So now you realize why I written that I, because the summation is over I. The summation is over all the data points. That's why I written it. Clear? Now there is a log of product which is equal to sum. So let us write that. So this is equal to 1 by n summation I equal to 1 to n summation j equal to 1 to k log p theta j x j I x less than j I. This is my final loss function that I am going to, not loss function, negative loss function that I am going to maximize. If I add a negative sign outside, then I am going to minimize it. So this is what I will do. Now there is a catch here. You can see that if theta j for each of the network is separate, that means each of the conditionals is having its own independent theta, then you can train it separately for each of the conditionals. Because when you optimize for, let's say, theta 2, you can assume theta 1, 2 other things to be constant. Those distributions will just be a constant term, and you can just work with that term which is having theta 2. So it will be able to do it, train it independently for each of the subnetworks. But that is not possible in NAID. Why? Because in NAID we do parameter sharing. So as soon as you do parameter sharing, whatever is in theta 1 is also there in theta 2. Whatever is there in theta 2 is also there in theta 3. And we discussed it that we will just add one row or one column, right? So that means in NAID you do not train it separately, you train the whole thing together. But in fully visible sigmoid belief network, this thing you can train separately. Okay, so when you get a homework, I will give you a problem in homework. Take a note. So when I give a homework, there will be a problem on this. We'll ask you to do it using fully visible sigmoid belief network, and that time you will see that you are able to train it separately. And we'll also ask you to write a code for NAID and to train it. And at that time, you'll realize that you cannot do separately. Okay, so this will become more clear when you actually write your own code. And that's why the homework and practicals are so important. Okay, but anyways, it is very intuitive and you can easily see that if I am optimizing for theta 2 only appears in probability of x2 given x1. no other terms will have theta 2. So those are constant independent of theta 2. Those will be like us one summation, right? One term which is like constant. Remove it. Just optimize that term, right? So that will be possible in this case if parameter sharing is not there. If parameter sharing is there, then it can't be helped. Okay. So this is your loss function. This is what we will be working with in autoregressive generative model. And this is independent of, you can see I have not assumed it to be continuous, I have not assumed it to be discrete, I have not assumed the network to be anything. I mean, even if it is generative transformer, this is the loss function. If it is NAID, this is the loss function. If it is fully visible sigmoid belief network, this is the loss function. This loss function or negative loss function actually will not change until and unless you change your KL divergence loss. If you use some other divergence, then this will change. Otherwise, this is only function of KL divergence, that loss. It is not a function of NAID or model change will not change this loss. Loss function change can change this loss. Okay. Any question? Yes, yes and no. Yes and no. Yes, because you are correct. It will be much easy to train. No, because what will I do with the training if it overfits? So I want to train and I want to train fast if I am getting the correct result. If I am getting the wrong result, then what is the point of training it faster? Right. So it you need to okay, there are two things, right? Parameter sharing, what happens is that parameter sharing helps you reduce the number of parameters, first thing, which means each of the network, the expressive power is reduced. Because the expressive power is reduced, it will not overfit. But because the parameters are shared, you have to train all the net parameters together. Because one parameter you can imagine is part of everything. But again, I mean, there are ways also. You can think about only training for the last one. That is only there in the last term. And but then you train for the second last, but that is in last two terms. So ultimately, at least it will not help much. I mean, you can think of some software engineering over this to make it more efficient, because you can imagine theta k will only be there in the last term. The theta k, the last row, last column, that will only be there in the last term. So if you train it separately, then you only need the last term. But then too much software engineering might be needed. So better train for everything. Okay. No, right? It's a Gaussian. Gaussian is infinitely differentiable and all of those things. So it's very easy. Unless and until you are working with a PDF that is not differentiable, then you are in trouble. But as long as the PDF you have assumed is differentiable, you are fine. So Gaussian is differentiable and all of those things, right? So is Bernoulli. So you are fine. But there are some distributions which are not differentiable. So in that case, this might be a problem. That was your only question, or there was another part to the question? Only difference, right? But there is one thing you need to keep in mind, that the loss function is actually function of all the training samples. But when if you try to compute gradient with all the training samples, it will go out of memory. Your GPU do not have that memory. So you will actually be working with the approximate gradient, which is the stochastic gradient. So you'll be using batch stochastic gradient descent. So again, that I have discussed in the practical. I'm not going to discuss that again, but you know that in practice the gradient will be based on a batch. It will not be based on all the data. And that's not because out of memory and computational reason, no other reason. Okay. Yeah. Ned. Yes. So basically what I'm saying is do some scheduling. Assume the other parameters to be constant, train for it, and then do some iteration and all of those things, right? You cannot do it exactly, obviously. Anything, anyways, nothing is exact. It's a non-convex optimization. But the thing is, there is a way, right? You can assume other parameters, initialize it, make them fixed, just update it, and then go back, keeping it fixed, update others, then come back. I mean, you can think of those iterative kind of scheme where it switches and all of those things. So in that sense, I'm saying. Okay. Okay. So that is it for autoregressive generative model for now. Remember that we will come back to this when we talk about GPT or GT, generative transformer, towards the end of the course. So that is the last thing we'll do in this course. Again, time permitting, you keep that in mind, but it is the last thing we'll do. But yeah, I think I have some slides here. So MAID, I was talking about MAID, right? Mask autoencoder. So this is the MAID architecture. We'll talk about it when you go to autoencoder. We'll again visit this one at that time, and we'll talk about this there. I've kept a slide here, but we're not discussing it now because we have not discussed autoencoder and VAEs. And yeah, so this is the GPT thing I was talking about. I kept one slide for that, but we're not going to discuss it today. That is for some other time. And again, the lecture notes and videos I'll upload this week. I mean, apart from one video which has some issues, so all of those things will be uploaded this week. The practical submission will also be uploaded or created, rather, I should say. Yeah, that's all. Okay, thank you.